Hello and welcome back to my series of videos on prime numbers, and today we're going to look at the last digits of primes. So all prime numbers except 2 and 5 end in 1, 3, 7 or 9. Well, we know 2 and 5 are prime and they clearly don't end in 1, 3, 7 or 9. Let's quickly prove that all other primes must end in 1, 3, 7 or 9. Well, any even number bigger than 2 is not prime, as it can be written as 2 times c, where c is an integer. So the evens are 2, 4, 6, 8, 10, 12, which is equivalent to 2 times 1, 2, 3, 4, 5, 6. So apart from the very first one, every even number can be written as 2 times something greater than 1. So that means all of those are not prime. Only 2 is prime, and I've put that in red. So that means apart from 2, only odd numbers can be prime. The sequence of odds is as follows: 1, 3, 5, 7, 9, 11, 13, 15 and so on. And they go up in 2. It's not hard to see that they always end in 1, 3, 5, 7 and 9. 1, 3, 5, 7, 9, and then 11 ends in 1, 13 ends in 3, 15 ends in 5, and so on. It just repeats 1, 3, 5, 7, 9, 1, 3, 5, 7, 9, keeps going, looping forever. Now those ending in 5 are not prime, except 5. So ending in 5, we have 5, 15, 25, 35, 45, 55, an arithmetic progression, common difference of 10. We can write that as 5 times 1, 3, 5, 7, 9, 11. So notice apart from the first one, they are all 5 times something bigger than 1. So all except 5 can be written as 5c, where c is bigger than 1. So that means apart from 2 and 5, all primes will end in 1, 3, 7 and 9. Well, technically I'm done. I've shown that all primes p bigger than 5 must end in 1, 3, 7 or 9. Why does this only work for odds ending in 5 and not 1, 3, 7 or 9? Good question. So let me briefly show you why. I won't go into too much technical detail. So 5 is a little special. Consider the sequence of all integers ending in 5. 5, 15, 25, so on. So it's an AP with first term 5, common difference 10. We can rewrite it as 10 times 0, comma 10 times 1, comma 10 times 2, all in a curly bracket, plus 5 equals 10c plus 5, where c equals 0, 1, 2, any integer. But we can rewrite that as 10c plus 5 equals 5 times 2c plus 1. So 5 is a common factor, pull it out, factorize it basically. So that's 5 times 1, 3, 5, etc. So 5 upon 2c plus 1 is the reason all numbers ending in 5, except 5, are composite, as they are the product of two integers, namely 5 and 2c plus 1. 5 is the exception, as if c equals 0, we have 5 times 1, which is prime. For all c greater than 0, 2c plus 1 will be greater than 1. Hence, 5 times 2c plus 1 equals 5 times n greater than 1. It won't work in general for 1, 3, 7 and 9. Consider the following sequences or arithmetic progressions. A equals 1, 11, 21, 31, 41, 51. B equals 3, 13, 23, 33, 43, 53. C equals 7, 17, 27, 37, 47, 57 and so on. And D equals 9, 19, 29, 39, 49, 59 and so on. You'll notice that these are all arithmetic progressions with a common difference of 10. Now I've highlighted the prime numbers in red: 11, 31, 41, 3, 13, 23, 43, 53, 7, 17, 37, 47, 19, 29 and 59. And I've just quickly checked, yeah, the ones in black are all composite, apart from one special, one is not prime or composite, but I just wanted to focus on the primes for a minute, so I've put them in red. So in that set A above, you've got a few which are prime and a few which are composite. In B, you've got a few prime and a few composite. In C, you've got a few prime and a few composite. And in D, you've also got a few prime and a few composite. And in general, this is what tends to happen. You'll have a mixture of primes and composites in each set. So this is actually a philosophical debate or an open problem. Clearly there are some primes in each sequence, and we know there are infinitely many primes. So if we pick a number ending in 1, 3, 7 and 9 at random, there's no guarantee it will be prime or composite. It's more likely to be composite, especially as we approach infinity, since primes get rarer. Clearly not all numbers ending in 1 or 3 or 7 or 9 are composite. There may be finitely or infinitely many ending in 1 or 3 or 7 or 9. They don't necessarily have to be uniformly distributed, i.e. on average roughly 1/4 of all primes end in 1, and same for 3, 7 and 9. Question: do all numbers ending in 1, 3, 7 or 9 eventually become composite? It could very well be possible. We know it can't happen for all ending in 1, 3, 7 and 9, i.e. every single one, as that would mean there are finitely many primes. But it could happen for at most 3 of them. So it could happen for, say, all ending in 1, 3 and 7. They could all become composite eventually, which would mean that every prime after that must end in 9, because we know there are infinitely many primes. It may happen for 2 of them or 1 of them. We don't know. We don't know. That is still actually an open problem. Another way of looking at it, does there exist a large n, and I mean very large, such that for all integers x greater than n, we have 10x plus 1 is composite, 10x plus 3 is composite, 10x plus 7 is composite, 10x plus 9 is composite. Have a ponder over that for a moment. So there would have to be some extremely gigantic number n for this to work. This is beyond our comprehension right now. It could very well happen. It's not been proven or disproven. However, we do know that there are infinitely many primes. So it's not going to happen for all of them. You wouldn't have all of those sets being composite for some large n. But it could happen for 1 or 2 or 3 of them. It seems unlikely, but we can never say never. But we can definitely say that for any integer x greater than 0 or equal to 0 and y equal 1, 3, 7 or 9, 10x plus y is not guaranteed to be prime or composite. There's no way to know for sure. So if you go back up to those sets we were looking at a minute ago, there's always going to be some reds in there and some blacks in there. There's no way to know for sure. Certainly for all the numbers that we've looked at and that have been studied. But for gigantic n, we actually don't know. So as I say, there's no guarantee. So for any integer x greater than 0, 10x plus 5 is always composite. That we do know. That we have just proved. That's very easy to see. But for the other ones, 1, 3, 7 and 9, no. It's not always going to be prime or composite. There's no guarantee. But for 5, it's guaranteed. So if p is greater than 5, where p is a prime number, it must end in 1, 3, 7 or 9. Now in my next video, I will look a little bit more deeply at this, at what's going on here, and discuss the concept of coprimality, i.e. a number being coprime to another number. This all ties in with primes bigger than 5, ending in only 1, 3, 7, or 9. So we're actually going to look a little bit more deeply to see why this only works for 5 and it doesn't work for 1, 3, 7, or 9. So there's a little bit more going on there that isn't totally obvious to the eye. So thanks for watching. Please subscribe and I'll see you on the next video.